Hi class, we continue talking about trigonometric integrals off the PowerPoint slide posted in your classroom, and we're on example 5 in this video. So for this example here, what I want to do is I want to find the integral of secant to the fifth power x dx. All right, now this one here, it's going to seem a little weird, but we're actually going to try to solve this by parts. All right, so what that means, I'm going to have to pick a u and a dv. So what I'm going to have as my u is I'm going to pick secant cubed, and my dv is secant squared x dx. And the reason I can do that is because u times dv gets me back to secant to the fifth power x. All right, that means du and v here, this right here, if I take the derivative of this, I get 3 secant squared x times secant x tangent x. And the integral of secant squared x dx is obviously just tangent x. All right, so just following our formula now. All right, the integral of secant to the fifth power x dx is u times v, so it's secant cubed x times tangent x, minus the integral of v du, so minus 3 secant squared x, well, times secant x gets me 3 secant cubed x, tan x times tan x gets me tan squared x dx. So now what I need to do is I need to integrate this. Well, what I'm actually going to do here is I'm going to sub in with one of the Pythagorean identities. For tangent squared x, I'm going to put in secant cubed x minus 1. Now watch what happens when I distribute here. Right, so this becomes minus 3. I have that, I'm distributing with everything. Secant cubed x times secant squared x gets me, this is weird, secant to the fifth x dx, plus 3 times secant cubed x minus, don't forget the minus here, times minus 1 gets me plus 3 the integral of secant cubed x dx. What you're going to notice here is like, well, this stinks. I just got another secant to the fifth power here, x dx. Well, I'm actually going to add this over to the other side. All right, I'm going to add 3 times this integral to this integral over here. And when I do, I get 4 because the integral of secant to the fifth power x plus 3, the same thing, gets me 4. Secant cubed x, tangent x stays. And this here, the secant cubed x dx, I'm going to skip ahead in the slides here, but the way you would solve this is you would have it as secant x times secant squared x. And then what you would do is you'd substitute in for secant squared x, 1 plus tangent squared x. And then when you do, this is what the integral just becomes. So then the final step, so on your own verify that this integral becomes this. The final step would then just be to divide the 4 over, and this is what you get for your answer. So for some of these, don't be afraid to, when you do by parts, to get back to what you had before, and then just add it over and divide the constant by. All right, let's try this one. So let's evaluate, find the integral of tangent squared x secant cubed x dx. All right, well, the first thing I'm going to do is I'm going to substitute in secant squared x minus 1 for tangent squared x. Now watch what happens when I distribute. I get the secant to the fifth power x minus secant cubed x dx. Well, guess what? I literally just did that in the previous problem. So I know what secant to the fifth power x integrates as. It integrates as this crazy thing. And then I know that secant cubed x integrates as secant cubed x integrates as this crazy thing. So let me just plug those in. And this is what you get for your answer. You can spend the time to combine like terms if you want on your own, and your final answer will just be this right here. All right, let's do 2 more examples, maybe 3. So let's integrate 1 minus tangent squared x divided by secant squared x dx. All right, here's how I would tackle this problem. The first thing I would do is I would bring outside the parentheses 1 divided by secant squared x, because that's like the thing that's making it difficult. Well, what does this 1 divided by secant squared x become? Well, that's just cosine squared x. I know that tangent squared x is sine squared x divided by cosine squared x. So let me distribute. When I do, this cosine squared x times 1 will just be cosine squared x. And then over here, it'll cancel, and you're just left with this. Now, there's a ton of ways you could solve this problem. What you could, the easiest thing you could do is you could immediately, I'll go through the hard way actually. You could immediately look back at your trig identities, but say you don't see that, all right? So remember how we got here, because in the next slide here, I'm going to show you an easier way than I'm about to solve. So here, what you could do is you split the integral like this. Then what you're going to have to do is you're going to have to power reduce both of them, because the squared is what makes it hard. Then when you do split it up as such, right, you split the 1/2 and then 1/2 cosine 2x, then minus, don't forget the minus, and all of this stuff here. And then you simply integrate both of this, right, distributing the negative first. When you integrate this, obviously you see 1/2 dx cancels with this. 1/2 of the integral of cosine 2x plus 1/2 the integral of cosine 2x is just the integral of cosine 2x. And that obviously is just going to integrate as 1/2 sine of 2x plus c. So you could do all this crazy stuff with the power reducing and splitting it up and combining like integrals. Or another way you could do this is when you're at this stage right here, you could recognize that this looks like a trig identity, all right? And this is actually just by itself equal to cosine of 2x, which is what we saw by simplifying it. And you just get that obviously. So if something looks like a trig identity, pause and see if it is. And then if it is, just plug it in and go for the integral that way. All right, let's try this one right here. So I'm going to integrate dx divided by cosine x minus 1. So it's like, well, there's no trig identity for this. How are you going to even solve this? Well, whenever you have something complicated in the denominator like this, you're going to multiply by 1. And what the 1 is going to be, it's going to be the conjugate of the denominator divided by the conjugate of the denominator. So the conjugate of cosine of x minus 1 is just cosine of x plus 1. And you can multiply both the top and bottom by that, because this is just equal to 1. Well, when you distribute, you get the following. Well, now I have a cosine squared x minus 1. That looks like a trig identity, and it is, and I can plug it in as minus sine squared of x. Now watch what happens when I split it up, right? Factoring out the negative here. What does this simplify to? What does this simplify to? Well, the top, I'm going to peel off from the bottom 1 over sine of x. Obviously, 1 over sine squared of x is just cosine squared of x. This right here, cosine over sine is cotangent. 1 over sine is cosecant. So 1 over, as I said, sine squared is cosecant squared x. Split it up into two integrals. And obviously, this first one, the integral of cotangent x, cosecant of x, integrates as minus cosecant of x. And cosecant squared of x obviously integrates as minus cotangent of x. So here, when it looks like something crazy in the denominator, multiply by the 1, where 1 is the ratio of the conjugate of the denominator. All right? Don't forget to distribute the negative outside, and that's your final answer. All right, let's do this one last one here. So let's evaluate cosine squared of sine of x. So that sine of x is inside the cosine function, times cosine of x dx. Well, you're going to need to use a u sub to start. So you're going to let u be the inside here of sine of x, and that means du is just this cosine of x dx. So now look what you have. By letting u be this, du is this now just becomes the cosine squared of u. Well, obviously the squared here, as you've been seeing throughout the videos, is what makes it difficult. So you're going to power reduce this. When I power reduce it, I get the following. Then all I'm going to do is I'm going to split this integral up into two integrals. This is very easy to integrate. This is also very easy to integrate. Then you get the following. You do. But now here's the problem. Now you have your answer in terms of u. So your last step is to remember what u was. and you plug it back in for u. So wherever you see a u, you're going to put in your sine of x. And that's your final answer. All right, we've done a ton of examples here, 9 examples here. So now there's just some general guidelines for a strategy to approach with this. All right, so whenever you have the integral of sine of n of x to the cosine m of x dx, you have the following. If n is odd, you're going to strip one sine out and convert the rest of the integral to only cosines, all right, using your Pythagorean identities. And then you're going to use a u substitution with u is equal to cosine of x. If m is odd, you're going to strip one cosine out and convert the rest of the integral to sines using your Pythagorean identity, and then substitute u is equal to sine of x. If both n and m are odd, doesn't matter, you can use 1 or 2. If m and n are both even, all right, you're going to use double angle, half angle, or power reducing formulas to reduce the integral into a form that can be integrated. So when they're both even, that's a little bit harder. All right, when you have integrals of the form tangent of nx times secant of mx dx, we have the following. If n is odd, strip one tangent and one secant out and convert the rest of the integral into secants using tangent squared x is equal to secant x squared x minus 1. And then the substitution of u is equal to secant of x. If m up here is even, strip two secants out and convert the rest of the integral to only tangent using secant squared is equal to 1 plus tangent squared. Then use the substitution u is equal to tangent of x. If m and n are even, both the top two methods will work. That'll be fine. If n is even and m is odd, each integral will be dealt with differently. All right, you're going to literally have to try trigonometric identities, substitution, or even integration by parts. But as you go through your homework, work on your study plan, try the homework questions multiple times. A lot of it will be just trial and error.